Hello, my name is Joris and I'm a PhD researcher with the NCCR Digital Fabrication from the chair of Gramazio Kohler Research at the ETH Zurich. On behalf of all of the authors, I'll present today our paper titled Design and Fabrication of a Non-Standard Structural Concrete Column using Eggshell Ultra-Thin 3D Printed Formwork. That was done in interdisciplinary collaboration between Gramazio Kohler Research, the Institute for Building Materials, and the Institute of Structural Engineering at the ETH Zurich. The presentation is structured as follows. First, I'll give an introduction and explain the concept of the Eggshell fabrication method. Then I will talk about the challenges we encountered when realizing the concrete column, speak about its design and fabrication, and then finish with some concluding remarks. If you look at the main building materials used in the world, wood, steel, and concrete, we can see that concrete is by far the most used one. More than 3 tons of concrete are produced per person per year, so very vast amounts. Most of this concrete needs a formwork for construction. This is often the highest cost of constructing a concrete element. This is especially true for non-standard concrete structures. It cannot be made with regular, straight formwork. For these structures, we can see that more than 80% of the cost are made up by the formwork. Often, non-standard formwork is produced by subtractive processes, such as CNC milling, and although this is effective, it is also wasteful. Additive formwork fabrication processes, such as fused deposition modeling, 3D printing, have the potential to increase geometric freedom with a low waste. However, addressing the lateral pressure from the concrete remains a problem for the thin formwork. One project that has effectively addressed the challenge of controlling lateral pressure on a formwork is smart dynamic casting, which uses a digitally controlled, set-on-demand material process that enables to control the hydration of concrete. With this, we arrive to the concept of the Eggshell fabrication method. Eggshell combines robotic FDM 3D printing with the set-on-demand casting strategy, such as developed during the project Smart Dynamic Casting. This can be illustrated as follows. On the left, you can see what typically happens when you pour concrete into a thin 3D printed mold. It breaks due to the lateral pressure. However, if we cast in the concrete using set-on-demand casting, adding one accelerated layer of concrete after another, we can use a thin 3D print as a formwork. The fabrication setup that we imagine to be used looks like this. A 6-axis robotic arm can be used for executing the movements, which then has an attached extruder as an end effector that is used for 3D printing the formwork. A concrete pump pumps the retarded concrete to a pin mixer, where the concrete is mixed with the accelerator. After acceleration, the concrete flows into the formwork while the formwork is being printed. Since the beginning of the Eggshell research project in 2017, many prototypes of varying scales and geometry have been fabricated, showcasing the potential for creating non-standard concrete geometry with a high resolution. We then got the opportunity to realize a first built example with the Eggshell fabrication method, a pavilion that combines 2 research projects at Gramazio Kohler, a robotically fabricated timber roof structure and a concrete column. The requirements for this project were to deliver a full-scale structural column that integrated reinforcement according to building norms and had heavy requirements on the exposure classes of the column. For the future tree, we had to develop a slightly different process, as the printing time was too slow compared to the setting time of the concrete to cast the column simultaneously. Therefore, in this consecutive process, formwork is first 3D printed, then is combined with the reinforcement cage, and then the formwork is cast using set-on-demand. This simplifies the process, however, it also puts constraints on the geometry that can be produced. Throughout the development process of the column, several challenges were encountered. The first challenge was the integration of reinforcement into the structures. In the early stage of the project, an attempt was made to use the simultaneous fabrication process and print around existing reinforcement bars. Although this method works, it also puts high requirements on the robotic setup that's being used, since printing around a full-scale reinforcement cage requires a large robotic setup and complex path planning. Therefore, this method was chosen to be abandoned. We therefore chose to pursue the consecutive fabrication process, as I explained before. However, it is not always possible to combine a prefabricated reinforcement cage with a formwork. For example, in case of this funnel shape, you cannot put a reinforcement cage inside after printing. We therefore adapted the geometry of the column so that the prefabricated reinforcement cage could be placed inside from the top. The second challenge was establishing the formwork design space. Here you can see one of the full-scale prototypes during the development phase, for which the formwork broke at the bottom while casting. In order to find out if geometry had an influence on the breakage, we then tested two different geometries for the bottom, a circular and an octagonal. To test the resistance of both against concrete lateral pressure while casting, we filled both of them with a set-on-demand concrete using the same filling rate. What we could observe is that in both iterations of the experiment, the octagonal formwork broke in one of the ribs at a concrete height of around 30 centimeters, whereas the circular formwork was able to be filled completely. This led us to choose for the circular cross-section for the column base. A third challenge concerned 3D printing the formwork in a large scale, especially in the top section, where it had a diameter of 1 meter. Here you can see one of the first tries of printing the top part of the column. Large delaminations between layers occur that are caused by shrinkage of the formwork. Shrinkage is a very common problem in 3D printing, and especially at a large scale, it is difficult to avoid. We then found out that the problem of layer delamination was especially apparent when printing long, straight sections. Consequently, by reducing the length of the straight sections, the effect of layer delamination could be reduced. We found out that by applying a micro pattern to the formwork with an edge length that stays below 70 mm, layer delamination could be avoided. And here you can see the same geometry as before, this time printed with the zigzag pattern applied. You can see that in this case, there were no effects of layer delamination due to shrinkage. In order to also increase the stabilizing effect that the pattern has on the formwork, the zigzag pattern was developed further into a diamond-shaped pattern. Both patterns were also tested on concrete prototypes, and the diamond pattern was chosen for the final design due to its increased stability. A parametric design tool was created that allowed for continuous adjustment of the design based on the new insights gained from the different challenges. Furthermore, it could also be used to directly generate the fabrication data. Throughout the development process, a total of 4 full-scale columns were attempted to be fabricated. With each prototype, new lessons were learned and improvements were made. Until the final prototype could be fabricated. Here you can see the final design for the column. What you can see is that the depth of the pattern increases as the column diameter gets larger, because the effects of delamination due to shrinkage are stronger. The design concept for the overall shape was so that the timber bars of the roof seamlessly transition to the concrete column. The formwork for the final column was printed over 26 hours, using a layer height of 1 mm, layer width of 1.5 mm, and PETG as a material. The column was printed using a combination of a robotic arm and a vertical linear axis to allow for greater build height. Then, the prefabricated reinforcement cage was lifted in. And the formwork was filled with set-on-demand concrete, casting in the concrete manually. We filled the full column over the course of 8 hours. Then we could take off the thin plastic shell by using a heat gun and pliers. And here you can see the formwork, reinforcement, and the final column side by side. The column was then shipped to site, and the timber roof part was added on top in 5 prefabricated modules. So now, onto some conclusions. It proved feasible to produce a non-standard reinforced concrete column according to building codes, with a 1.5 mm thin 3D printed formwork. Also, we were able to achieve a formwork to structure weight ratio of 1 to 100. So with a formwork that weighs only 8 kilograms, we were able to produce a column with a total weight of 800 kilograms. And here in this picture you can also see the intended design concept, with the timber bars flowing into the concrete column. But we also realized that the biggest challenge in this project was the reinforcement. As the formwork was 3D printed, this was made to millimeter accuracy, but the reinforcement gauge was manually welded together and therefore only had an accuracy of centimeters. It therefore proved very challenging to combine the reinforcement and formwork. And for this reason, I think it's essential that we develop new methods of integrating reinforcement into digitally fabricated concrete structures, especially if we are moving towards structures that are even more complex. Lastly, I would like to thank everyone that was involved in the project, as well as our industry partners. And I thank you for your attention, and if you have any questions, I would be happy to answer them.